Hi, I'm Alistair, and I make puzzles for escape room games. And in this video, I want to teach you how to make this puzzle, which is something I've seen used in a couple of different escape rooms. And to solve this puzzle, what players need to do is enter a secret rhythm of some sort. And the most common way I've seen that players have to do that is to knock a secret knock pattern to unlock a door. So that's what I've got set up on the board at the moment. At the bottom here, I've got a 12-volt maglock, which is securely locked. So imagine that is closing a door off. The power to that is being controlled by a relay module up here, and that is triggered by an Arduino, which has a piezo sensor here. So if I just knock on the board a few times, what you'll see is the blue LED go up there. That wasn't the correct pattern though, so I get a little sad tone from the buzzer. I'll try again. Happy birthday, maybe. No, that wasn't the correct pattern either. The correct pattern at the moment, you can set it in code to anything you want, but I've got it set to the very common pattern shave and a haircut 2 bits, which goes like this. And when the puzzle is solved, the maglock releases, falls on the floor, and the door is unlocked for the player. Now in that example, I was using the piezo sensor to detect the vibrations on the door caused by players knocking, and using that as an input to the Arduino. But of course that's not the only way that players might enter a rhythm. In this example here, I've connected a microphone instead of the piezo, and that's going to detect any sound input in the room. So suppose you had an escape room that was themed in a jungle setting, for example. Players might come across a set of jungle drums, and maybe they have to enter a rhythm that is copied from a background soundtrack in the room, or from the drips of water from a waterfall, or something like that. There are other well-known rhythms as well. Here in the UK, about 10 years ago, there was a very widely publicised advertising campaign, and if I showed you this image of a gorilla sitting at a drum kit, a lot of people might bring to mind the drum solo from Phil Collins's In the Air Tonight. So that's the solution I've got there at the moment. I haven't got a drum kit, but I have got some bongo drums. It goes a bit like this. And, oh Christ. And so you can use the microphone instead. So let me just talk through how these components are wired together. So here I have my Arduino, and I've got my various components here shown on a breadboard. So using the example of a microphone input to start with, because that gives slightly simpler wiring, otherwise they're pretty identical. So the microphone I'm using here is a Keys KY038 microphone. These are very easy to get online. They only cost a couple of dollars. And the inputs they have, so they have a 5-volt input here, going to positive. They have a ground as well. So I've got these going to the rails here, which are going to the Arduino 5-volt and ground. And they also have both a digital out and an analog out. Now, the digital out, that would just change from a high to a low value depending on a threshold amount which is set using this potentiometer on the module here. But I'm not using that. Instead, I'm using the analog output, and that's actually going to give me a whole range of responses depending on the volume that the microphone picks up. Now the reason I'm doing that is because when the code runs, what I'm going to do is I'm actually going to record the ambient level that the microphone picks up in the room. So just the background volume that there might be picked up by the microphone. And I'm going to set that as a kind of a base reading. And then if the value picked up changes by a certain threshold from that base reading, that's what I'm going to use to detect that a knock has been made by the player. So it just allows my code to be a bit more flexible and a bit more sensitive, and I can change those values very easily in code to kind of fine-tune how sensitive I want that to be. Now at the top here I've got 2 different outputs essentially. Now neither of these are actually required to make the puzzle work, but it's quite useful to have some kind of feedback mechanism for the player after they've entered a knock, just to let them know that it's been detected or not, and also for you to know the correct pattern that's meant to be entered and things like that. So these are just sort of non-essential but useful feedbacks. And the first one, I've got an LED here. This is plugged into pin 13 on one side through a 220 ohm resistor and then back through to ground. So that's a very standard way of plugging in an LED on an Arduino. Most Arduino boards actually have an LED on the board anyway, which is already driven by pin 13. So all this is doing is kind of extending that and making it more visible. And I've also got a buzzer here. And like the LED, the buzzer has got a wire to pin 12 in this case, and then going through a resistor back through to ground. Now the resistor in this case though is a bit higher. This is a 165 ohm resistor, and I just want to quickly explain how I got to that value. So an Arduino runs at 5 volts, but it is only capable of sourcing or syncing about, well, 30 to 35 milliamps of current really through any of its GPIO pins. So we need to ensure that the current that's flowing from pin 12 here through the buzzer and back again is under that amount. Now the buzzer itself has a certain amount of inbuilt resistance, so I took my multimeter and measured the resistance between the signal and the negative pin there and came up with a reading of about 15 ohms. If I add a series resistor in of 165 ohms, so the total resistance in this circuit is now 180 ohms. So we've got an Arduino running at 5 volts and we've got 180 ohms of resistance. So using the formula I equals V over R, which is Ohm's law, we can get 5 divided by 180 is 28 milliamps of current. And that's under the kind of, like I say, 30 to 35 milliamp comfortable amount. The absolute maximum rating is 40 milliamps, but I would keep it substantially lower than that if you can. You don't want to strain your input and output pins by subjecting them to something as high as 40 milliamps for anything more than an absolute briefest amount of time. And then the output here I've got at the bottom, so this is a 5 volt relay module here. On this side I've got a separate DC power supply. The negative side of that is powered to the maglock directly. On the positive side I've got going to the common pin on the load side of the relay, and then I have the normally open side connected to the other side of the maglock. So when this is powered off, obviously the normally open and the common side are not connected, so this maglock is going to be off. When the maglock is powered and switched over to the other state, these two pins will become connected and the maglock will receive power. That's controlled on this side of the relay, so we have 5 volt and ground supply. That's what's going to energize the relay coils, so the actual magnetic coils in here that's going to cause that to flip over. That's the supply there. And then this third line here, this is the signal line, which is going to pin 4. So that's what's actually going to send the high or low signal to make the relay switch between states. And here's the circuit layout for the Piezo input, which is almost identical. Like I said, it's got the same LED, same buzzer, same relay. The only difference is now that instead of having the microphone module, which had 5 volt ground and a analog output, I'm using the buzzer in its place here, which just has ground on one side, and then the analog input I've still got going to A0. But I do have a couple of other components here, and I just want to explain what those are for. So this one here, this is a Zener diode. So to explain the way the Piezo works, Piezos you might be more familiar with used as outputs. So they're the things which make buzzers work, and by applying a current to the Piezo, what it does is it causes crystals to kind of squeeze together or vibrate, and that can make a buzzing or a vibration of the air molecules. So that's how they work as a buzzer. But they also work the other way around. So by vibrating a piezoelectric crystal, you get a voltage in return, and that's what we're going to be using. Now that voltage can actually be surprisingly high. It doesn't have very much power, but it's actually got a very high voltage. It can be anything up to about 90 volts even. And remember I said before a little bit about the limits of the Arduino. The Arduino, you don't want to supply anything higher than 5 volts into one of its pins, or you'll blow the pin up. So the way this a Zener diode works is you get it pointing this way around. So you have the line pointing towards the positive side, and the other side goes to ground. And when the voltage is low, it kind of it's invisible in the circuit. It doesn't really have any effect. But if you were to kind of, you know, smash the piezo with a hammer or something like that, so drop a really big brick on it, and suddenly there's a massive voltage surge, what will happen is the Zener diode will effectively short circuit and create a path straight through to ground this way, providing us a safe way for that very high voltage to dissipate rather than going into the analog input pin. So they come in different ratings. This is a 5.1 volt Zener diode, which is the sort of the closest rating to what you're going to be able to get. And if what's called the Zener voltage exceeds that, so if the voltage across the pins of the diode exceeds that amount, it's going to short circuit and will create a safe way to lose that voltage rather than risking it all going into the analog input pin. The other component here's another resistor, and this is actually a very high value resistor. This is a 1 mega ohm resistor. And the reason for that is because even when the voltage isn't exceeded, so without using the Zener diode, we need somewhere for the voltage that's created by the piezo to go to, effectively. We need to discharge it. So if you think of this like a capacitor, you kept on hitting it, you're going to kind of build up this voltage over time. So the resistor is there to provide some way of kind of draining off the voltage created by the piezo and to create a safe amount to be read by the analog input pin here. So what the purpose of both of these essentially is to create a safe value that can be read between 0 and 5 volts on the analog input pin here. But anything that exceeds that amount, we're going to protect our Arduino by taking it through to ground. Other than that, it remains identical. It's an analog input, just as the microphone was, and we use it in the same way. And here's the code that's running on the Arduino. Now, this is quite a lot of code. I think it's one of my longest programs which I've done a tutorial on yet. It's got about 439 lines of code in total. So realistically, I'm not going to talk through every single line. As you can see, I've made quite a lot of comments all the way throughout. So if you, I mean, you're very welcome to copy it down, or else if you go to my Patreon, obviously my patrons will be able to download it anyway. But I will talk through it, and I'll try to particularly focus on the interesting bits that make it work. So first of all, obviously defines, always do this on all my code. I define a debug statement that's going to chuck out extra information that's going to make it easier to debug if anything goes wrong. In the next section, I define all the pins which are going to be used throughout this puzzle. And then I also define the pattern which I'm going to be using. So I've done a couple here already, you can see. So this is Shave and a Haircut 2 bits. I've got the In the Air Tonight drum solo I just did, and also done Happy Birthday to You. And in each case, I'm going to set up 2 variables. The first one is an integer that just says the total number of knocks that are going to be in that pattern. And then the next one, the actual pattern itself. Now, what this is a little bit complicated. This records the delay in between each knock in the pattern. So that's why there's one less element in it than there is actual knocks. So with 10 knocks, you've obviously got 9 gaps in between those 10 knocks. And the numbers here have been normalized so that the longest gap between any 2 knocks in the pattern is going to be 1024. So supposing you just have, if you're a musician and you think in terms of breathes and semi-breathes and crotchets and quavers, if you say 1024 is the length of a semi-breve, let's say, then 512, so that's 4 beats. 512 is going to be your minim, that's 2 beats. And then you go to 256 for your crotchet, then 128 for a quaver, 64 for a semi-quaver, etc., etc. So it's just a way of expressing the pattern in a way that's completely tempo independent. So I don't want to actually record the actual length of time between knocks in milliseconds, let's say, because if I do that and then the player enters it at a slightly different speed, it's not going to get registered as the same pattern. So that's what I mean when I say it's been normalized. So if you want to enter your own pattern in here, that's absolutely fine. All you need to remember is, like I say, the longest gap is 1024 and every other gap should be fractions of that. Okay. In practice, if this is going to be a puzzle that you expect players to be able to do anyway, you want to keep your rhythm pretty simple. So I wouldn't expect you to have anything more complicated than perhaps 1024, 512 and 256 in there. So that's your 3 different speeds of beats. Okay. In the next section here, so I've got some variables that are going to adjust the way the puzzle works. So the first one is going to be the threshold, and this is the amount by which the reading, the analog reading that's coming from either the piezo or the microphone, needs to change in order to be registered as a knock. Now, if you're using the microphone method, you particularly want this value to be quite high. A higher value is going to mean that it's less sensitive. And the reason for that is obviously a microphone is going to pick up any noise in the room, just people talking, walking around, or just banging objects around. And you don't want that to be detected as a kind of rhythm pattern that's being entered for this puzzle. So you want that threshold to be quite high, and also whatever device it is that they're going to be using for making the noise for this puzzle, you want to be quite loud as well and close to the microphone. If you're using the piezo sensor, it's less important to have that high. You can have that a bit lower, which will make it more sensitive. But you'll just need to try adjusting that yourself so that you get a reliable input that picks up everything it's meant to, but doesn't pick up excess noise as well. And then the next 2 values, these are going to be tolerances as to how much how different the pattern the player enters can be from the correct pattern and still be accepted as correct. So, most people don't beat out a perfect rhythm. They're going to be a little bit sloppy. They might get a bit behind some of the beats, a bit in front of some of the others. And these 2 values here change how much error will be accepted in the rhythm and still be accepted as the right answer. So this one here, this is if any individual knock is more than this value out compared to the correct delay here, then it will be rejected. So that's the individual knock tolerance. And then this is the average knock tolerance. So if at the end of the pattern the average amount by which all the knocks are out is greater than that, it will be rejected as well. The pattern also needs to have the correct total number of knocks in it. So those are kind of the 3 tests that we're going to use to check whether it's actually the right entry or not. And then we've got 2 timing values as well. So the first one, again, it's another method to get a clean signal. Basically, this is going to be a delay in between each reading. So the minimum amount of time that's got to elapse after one knock before the next one will be detected. Now, I tried sort of knocking as fast as I could, which is something like that. And when I measured that, that's about 480 beats per minute. So that corresponds to 125 milliseconds, which is the value I've put in there. So in practice, anything that is recorded that is more frequent than that pattern is probably like an erroneous double knock or something like that. So it's just going to help get rid of those. And this is the maximum gap between knocks. So what this says is that if there has been a longer delay than this amount after the end of a knock, then we're going to assume that the player has finished knocking and we're going to interpret the pattern that they have entered and compare it to the real one. I've set up a little variable here to allow you to use two different types of maglocks. In the example I'm shown in the video, I'm using a fail-safe maglock, so that's the one that needs to be constantly supplied with energy in order to stay locked. And here I've just got a couple more global variables. So this is going to be, remember I described the base reading, so this is going to be the reading that I get from the ambient level of noise in the room, or the ambient amount of vibration when the puzzle is not being entered. That will actually be calibrated in the setup function in a minute. And this is going to record the pattern of knocks that have actually been made by the player. So we're going to set up, initialize a serial connection, just output a bit of debugging information, set the pins to input and output as appropriate, and then the first thing we'll do, we'll actually play back the knock pattern that has been set at the top of the code there. So I'm going to call this function Playback Not Pattern, and we'll pass it in the value of the secret knock pattern that's been set. I'll show you that function in a moment when we get to the end of setup. We'll initialize the lock, so depending on the type of lock you're using, we're either going to send a low signal, that's going to lock it in the case of a fail-safe lock, or in the case of a fail-secure lock, we send a low signal for a little bit and then set it high. The reason for that is when you're resetting the puzzle, if you have a fail-secure lock, this is one that stays locked by default, even when it's not powered. And if for any reason you forget what the knock pattern is or something like that, it's quite useful to actually still be able to get into whatever cupboard door it is you've closed up. So this means that on power up, it will just briefly unlock the lock and then it will lock it again if you're using a fail secure lock. Then this section here, so this is where we're going to take 10 sample readings of the level of noise in the room. We're going to add them up, and then we're going to divide by the number of readings to get an average sample, and we'll use that as our base reading. Okay, that's the end of the setup function. I will just quickly go and show you that playback loop function that was called halfway through that. So when the puzzle starts up, in the setup function we'll call the playback not pattern function and we'll pass it in the secret knock. And what this does here, so this uses the combination of both the LED and the buzzer just to play back what the correct pattern is. So we send a tone to the buzzer and we also write to the LED, and then we turn them both off. So that's our first blink or buzz. And then for all of the remaining knocks in the pattern, we loop over them, and so long as there is something there, so it's greater than 0, we'll delay by whatever the correct time. So this is the unnormalizing process. Remember, the secret knock itself is normalized in a value between 0 and 1024. What we're now going to do is kind of expand that outwards again to an unnormalized value. And when I called this, I think I called this at 500 was the value I called it from setup. So if you change that value, it's going to play it back faster or slower because it's expanded it back to different amounts. We'll delay by that amount of time, and then we'll blink and flash the LED, and we'll just keep on doing that for all the knocks in the pattern. So that's what that function does. Okay, let's get back up to the top. So we've finished setup. We'll now get into loop. So this is the main program loop that's just going to go over and over again. And what we're going to do is we're going to test whether a knock has been detected. That seems like a reasonable place to start. The knock detected method itself is down here. And I've actually left in a commented section here. This is if you do have a digital input of any sort. So let's say that instead of a microphone or a piezo, you just wanted to have a button of some sort and have the players press a button in a certain rhythm. If you wanted to do that, you could use code a little bit like this that simply checks the value of the button and returns true or false. Or if you're using an analog sensor like the microphone or the piezo, as I have been doing, you want to use this section of code instead. So what this does is it takes a reading of the sensor pin. It compares the absolute difference between the current reading on the sensor pin and the base reading, and if the absolute difference is more than the threshold value that's been set, we'll say, yep, that's a knock. Otherwise, it's not a knock. Okay? So, if that has been detected, if our threshold has been exceeded, what we'll then do is we'll call this method here, listen to knock pattern, and that's going to carry on listening for further knocks in the sequence. So let me show you that one. I apologise for jumping around a bit. Like I say, this is significantly more complicated code than in other projects I've used, so there's a bit of jumping around. So if we're into this method here, we know we've already heard one knock because that's what triggered this off. So we're listening for the rest of the pattern. That's what it basically means. So what we'll do is we'll record the time now. That's what millis does. It will give us the number of milliseconds that the sketch has been running for on the Arduino. And we'll just blink the LED because that's what we always do, just to show that a knock has been registered, to get that visual feedback for the player. And then what we'll do is we'll clear out this input pattern. That's the array where we're going to store the value of all the delays between the knocks entered by the player. So this memset means to take the input pattern and to fill it with zeros for the whole of the size of the pattern. That's what that does. And then we'll keep track of the number of knocks that the player has entered. Like I say, we already know that there's been one knock because that's how we entered this function in the first place. And we'll carry on listening. So this is a little bit complicated here. So if the time now minus the last knock time, so that's the time that's elapsed since the last time we heard a knock, if that's less than the maximum gap, and also if we haven't yet exceeded the total number of knocks in the pattern, then what we'll do is we'll carry on. We'll get the current time. And if another knock is now detected within this window, so that's another knock to add onto the pattern. We haven't got as far as the complete pattern yet, and we haven't exceeded the maximum time either. So we've got another knock to add onto the pattern. And we enter this section. So what we'll do is we'll record the difference since the last knock was heard compared to now, because remember that's what we're storing in this array every time. It's the gap between knocks. So we'll work out what that gap is. We'll add that onto the end of the array. We'll increment the knock counter, and we'll also update the current time, and we'll flash the LED one more time. And we keep on looping through this section. So this whole section here, from here to here, we will keep on going through for as long as we haven't got up to the total length of the pattern yet. That's that condition. And also so long as there hasn't been such a long gap since the last knock entered that we think the player's got to the end of the sequence. And then we just do a little debug line at the end. Okay, let's go back up. So that was being called from loop. And it was being called here. So once we carry on, what we know now is that the pattern must have ended, and what we then do is we normalize it in order to be able to compare it to our stored knock pattern. So normalized pattern, that is down here. So what we do, this is actually quite straightforward. What we currently have stored in our input array is the unnormalized, the raw values in milliseconds of the gaps between each knock. And what we'll do is we'll loop over all that array, and we'll just keep track of what the maximum value was that occurred in that time. So as we loop over, if any delay is longer than the known max interval, we'll update the max interval. And then what we'll do is we'll loop over the array one more time. And this time what we'll do is we'll remap, so we'll use this map function to take the value from whatever the maximum knock interval was recorded in the data. We'll rescale that down to 0 to 1024. So that was the scale in the raw data from 0 to max knock interval, and this is going to be the scale in the normalized data, 0 to 1024, and then we'll reassign that back to knock pattern. So, like I say, the purpose of that is to be able to compare two different patterns that are entered, even if they might have been tapped at different tempos. They will still be considered to be the same. We'll just do a little bit of debugging there just to check what the timings were. And then what we do with our normalized input, we compare our normalized input to the secret knock pattern we assigned at the top of the code. So let me show you what compare pattern does. Compare pattern is down here. So there are 3 tests in total that we're going to go through to decide whether the input pattern matches the secret knock pattern. The first one, nice simple one, has it got the correct total number of knocks? So this is a really simple one to do. We loop through the input pattern and we check that from I0 to I's number of knocks a pattern, that there is at least a delay of greater than 0. If there's 0, it means that there hasn't been a knock received, but anything greater than 0 means that there was a delay and there was another knock afterwards. So if any one of the values in the input pattern is 0, that means that it didn't have the right number of knocks and will reject the input there, so we'll return false. The second test we're going to do is were any of the individual delays between knocks in the pattern outside of the threshold we defined at the top of the code for allowable error. So again, we'll loop over each of the knocks in the pattern. We'll find out the absolute difference between the delay that was entered by the player and the ideal delay in the pattern. And if that difference is outside of the allowable tolerance, again, we'll reject the pattern, so we'll return false. And then the final test we'll do, in that previous function there, we were actually adding up the total amount of error as we were going through, the total error in every delay between every knock in the pattern. And what we'll do is we'll divide that by the number of knocks in the pattern to get a kind of an average kind of sloppiness rating, I guess, as to how good the pattern was. And if that is outside the tolerance we suggested, then we'll return false. If we get to this line here, it means that all 3 of those codes so far have, all 3 of those tests, sorry, have passed, which means that we're going to say, actually, this was the correct pattern, and we will return true. When that happens, we'll go back up to our loop code again. So we have 2 possible outcomes from the compare pattern. If it was true, we go to the onPuzzleSolved method. So the correct pattern's been entered. We'll play a little happy chirp from the buzzer. And again, what we'll do then is we'll release the maglock. There's 2 different versions of code here, depending on whether you're using a fail-safe or a fail-secure maglock. If the output, or if the result returned from compare pattern was false, that means that we go to this section instead on incorrect input, and this time we'll play a sad chirp, ooh, and we'll angrily blink the LED to let the player know that it was incorrect. And that's it. So there is quite a lot of code to get through there, but congratulations for making it through to the end. I hope you found this video useful and helpful. If you've got any questions or comments, please do let me know below. If you'd like to grab a copy of the download of the code and also the list of materials and everything which I use to make this project, please do head over to my Patreon page, where you can find all the resources to go with this and every other puzzle tutorial I've done. And thanks very much for watching, and I'll see you next time. Okay, bye.